As you can see, we have a glorious network so far. Here is our original ground density that we sourced. Here is us establishing that combustion shape, and then also our velocity over here. That brings us to having fuel temperature and velocity in these fields. Now, the next step is to add a bit of density and also a bit of noise to all these fields while we're at it. Noise to everything except for velocity, because that's good to go. So we already have this guy that's adding noise to fuel, and we did that earlier. But I'd also like to add a cloud noise right here. So let's start off by going here and doing a cloud noise. What we'll find is that we don't see anything. And why is that? Well, because the cloud noise is a little bit silly and it doesn't recognize any field besides density. So that means we have to create a primitive wrangle and rename our fuel field to density so that the cloud noise SOP works. So @name is equal to density. As soon as we do that, there we go. We have a cloud. Let's turn on our high quality visualization right here and also set down a pyro bake volume so that we can actually see what this is doing. So if we do that, turn up the density scale quite a bit, and we can turn this up as well. Now we can actually see what these shapes are. On the cloud noise, this is before, this is after. It kind of adds a bit of extra noise on the exterior portions of this. So if we turn up the amplitude to, let's say, 0.25, maybe the octaves up a couple of notches, and then the element size down just a tad bit, right around there. It'll add a lot of higher frequency detail, and especially these little puffs out here, that will add a lot of extra detail to the actual plumes themselves. So that's what we want. Turn up the roughness, and that's pretty much good. We can also go to advection and turn up this amplitude if you'd like, but for the most part, we're just trying to get these little bits of extra high frequency detail along the outside. Now, we'll do the same exact thing for the temperature over here. So let's take this and call it density, which again is used because the cloud noise doesn't know any better. Once we have this cloud noise, plug in the visualization, we want to simply offset this noise. So that will give us a different version of the noise. While we're at this offset, it also makes sense to animate this so that it moves really quickly. So let's say $t times 20 in the Y direction. If I go through here, each frame, we should see a pretty significant change at each frame on what this noise is doing. And so that'll add a lot of extra detail here as well. Let's go ahead and copy this parameter and bring it over to our original cloud noise just in the Y. So we have this for our fuel, this for our temperature. They move around. That's really cool. Let's now rename this guy over here back to temperature. So we have this, and we will say temperature, which is right there. Cool. Same deal now for density. All we need to do is just make a copy of all these guys, and we don't need to rename anything differently after the cloud noise. We just have to plug it in. So plug that in, set all the wires straight by doing this sort of thing, and last but not least, change the offset here so that we have a different seed. Okay, cool. So density, fuel, temperature, good to go. One last thing, we have this Sourcify subnet. And the thing about the Sourcify is that this is not a perfect tool yet. I mean, if you want to turn this into a tool, you'll have to go and make user parameter things and maybe think about this workflow a little bit more, see how you can make things more procedural. It's not perfect, but once you know the system, pretty much all you need to do as far as manual work is paint the directions that you want things to go in. So That's really not so bad. I like having a little bit of that manual process in there because usually clients would be rather particular about where they want the initial explosion to go, or at least they don't know that that's something they want, and it's cool to just be able to paint exactly what you want there. So anyway, that all being said, if you do want to turn that into a tool, it'll need some work, but I'm just going to copy everything we have right here again into our Sourcify subnets, and this will be cached out as our combustion cache. Let's now see what happens when we bring this into Axiom. First thing that we ought to do is take this velocity value and set that to 40 so that we can really see this in action to make sure that it's there and working. If we go to scrub forward here, we end up with this. And it looks like we did have a little bit of action going on at frame 30, but not a whole lot. So just to really isolate that velocity, let's go ahead and take temperature down to 1, combustion, take that temperature down to 1 so that we're really just looking at that velocity sourcing and seeing what that's doing. Okay, so frame 30, there we go. We have something like this. It's still not doing a whole lot though. So what happens if we go to 100 on that velocity sourcing? Well, it's kind of working. We might need a play blast to really see what's going on here. So let's do just that. I'll do a play blast from maybe 1 to about 90. And with a velocity of 100, we don't really have that impact happening nicely here either. At least some of this is kind of more instantaneous. It's not perfect, but it's better than what temperature was doing. It took temperature about 15 frames to show up as anything. So at least velocity is getting us somewhere better. What happens if we bring this up though? So let's say if we go to 200 on that. We're going to start running into some problems with mushroom clouds, but let's check this out. All right, and at 200 we have a slightly better impact, but it still just isn't hitting very hard. We're getting these really blobby shapes. And a lot of times when you have these blobby shapes, it's because things are moving fast and you don't have enough substeps to figure it out. So the faster you make this, the more blobby these puffs are going to be. And just to show you how this really can turn into a blob, I set the velocity to 2000. And look at this. Now we're really just blowing this out of the park. We're getting that initial motion that we want, so maybe this is the right speed at first, but now all of our calculations are totally off, and you would need a lot of substeps to figure out this particular motion right here. So how do we fix this, and how do we keep the simulation intact while getting that fast motion when it first hits? Well, there's a couple of tricks to this, and they're not so obvious. Unfortunately, this is where we start running into limitations from the Axiom solver. Because in our DOP network, so if we create a DOP net, we have this thing called a gas repeat. So this gas repeat solver will repeat calculations. So the way that this works is that you could repeat the velocity calculation and the temperature calculations a few times to get them warmed up and to add more into the simulation at specific times of the simulation. And it doesn't create that bubbly effect. So this gas repeat solver is a great way of getting that initial impact without extra substeps and without all the extra hassle. So I'll show you this when we build our sparse pyro solver, and this is my preferred way of going about this. However, if you're working with the Axiom solver, there's another way to fake this. So what you do is you source things in normally. So let's say our velocity is 50, our temperature is 50, and maybe we can go down here to our combustion and bring some temperature in as well. So 50, maybe a pressure of 2. Something like that, right? And we go do a file cache for that simulation. Well, the idea is that we take those cache files and we rely on the retime node to retime that initial impact so it's really fast. So let me show you what I mean here. I'll cache this out and then we'll check out the retime. Okay, so after doing this for 120 frames, we have this plume going on. Not perfect, obviously, a lot to be desired with this. However, we do get that velocity, the temperature is in there as well. It looks like it kind of finally gets going right around 45. That's when the temperature really kicks in. What we can do is use a retime and fix that. So it works with this retime. There's also a lab retime as well. So a lab's retime right there. And this might also do the trick. I've had mixed results with this, but sometimes this lab retime is nice as well. So you go through, let's say here, right? And at frame 30 things start. Well, if we turn these into Bezier curves, we can give ourselves a little bit of an extra boost at the beginning like this. So it kind of starts and then it kind of chills out like that. And this is not a perfect way of doing this, but you would basically bring this over like so until we hit 30. And as soon as we hit 30, boom, that's where we have that impact happen. So I'm going to play blast this and I'll show you the difference. All right, and now at frame 30, we get that action a lot better. It's still not perfect. It's, not an ideal way of going about it, but you can kind of fake that impact a little bit. And obviously you'd want to dial in how this, falls off into its normal motion, but the impact itself is improved. So that's another way that you could potentially go about this if you're using Axiom. However, my preferred way, again, is to use that gas repeat solver. And there's a few reasons for that, but I'll show you that once we actually build out the sparse pyro. Really, at this point, I think it's time we move over to the sparse pyro because we've sort of hit the wall here with Axiom when it comes to this. It's pretty important to get the timing of that impact correct and how we want it to be. And also, there's going to be a few other features that Axiom can't support, like doing some vorticles spinning around in here to break up those mushroom clouds, and to have some debris falling out of the plumes and stuff like that. So we're going to, in the next video, switch this over to a sparse solver setup and go from there.